Okay, I'm Nalene Villiers, and I'll be presenting Invent Yourself. In this presentation, I'll be going over my assumption from the question, the theory, the equipment and method involved within the experimentation, and the results, which will then come to my conclusion. So, the problem states it is more difficult to bend a sheet of paper if it is folded accordion style or rolled into a tube using a single sheet of A4 and a small amount of glue if required. Construct a bridge spanning a gap of 28 centimeters. Introduce parameters to describe the strength of your bridge and optimize some or all of them. So this is the diagram, a free body diagram of when we were actually doing the experimentation. We put the force down in the middle of the bridge, and I'll explain why later. So our assumption from the question is that, our own assumption is that a bridge fails when it collapses. It can no longer sustain its original maximum force, which you'll see in the results why that is. That the paper can be bent, folded, and placed in any way as long as it's 28 centimeters long. That is to to cross over the gap. But the problem doesn't actually state anything about folding or placing it. So, a theory. It's called flexural stress, which flexural stress is the internal load that a bridge is subjected to when a force causes it to bend perpendicular to its long axis. That's if the bridge is a beam, it's along the length of the beam. And flexural strength, which is related to stress, is the property of a solid, which indicates its ability to withstand bending. So how much force it can take before it starts bending or just collapsing. So this is the equation for flexural stress. Flexural stress is equal to moment in engineering, which is torque in physics, times y, which is the height of the object, the surface, from its axis, from its central axis. So this would be y if our bridge were a beam like this. And I is the area moment of inertia, which is an object's ability to defy deformation. Area moment of inertia has its own equations. The main one we used, the main one that we connected to our final results of the strongest bridge, the one that optimized the most, is this one, but there's also other equations for area moment of inertia. Oh, sorry, I forgot to explain. This is area moment of inertia. This is the area moment of inertia at the center of mass of the object. A, in this case, A is this dark blue area in the object, and D is the distance from the axis to from the axis to this point. So this would be D. Not to be confused, J and IX are actually the same thing as I previously. It's just that for different shapes, there is different equations for the moment of inertia. So, for area moment of inertia for a hollow cylinder, this is the equation for the area moment of inertia, and this is for a solid triangle. Going by the definitions, a bridge collapses when a flexural stress is more than the flexural strength, because the flexural strength is how much force a bridge can actually take before it collapses. So if we have more flexural stress, it's how much stress it can take before it collapses. So if there's more stress than the bridge can take, then in theory the bridge should collapse. So to optimize a bridge's strength or flexural strength, we have to try and make the flexural stress as small as possible so that we keep this crocodile mouth on the other way. And the area moment of inertia has to be as large as possible because if we look in the equation, my is divided by I. So the larger I is, then the smaller our result will be. So in the experimentation, we used a ruler for calibration when tracking, a force sensor because first of all it's very efficient because we get data inputted straight into the computer, and also it keeps like the contact surface with the bridge constant. Otherwise, if we're doing